All right, so we're talking about end behavior of polynomial functions here. This is a very similar table to one that we had last year, where we described the end behavior just based on two things, whether the power was even or whether the power was odd. That's happening up there. So the columns are based on whether it's even or odd, and then the coefficient being either positive or negative out in front. Will tell us exactly what the function is going to do as x gets really, really big or really, really small. So we're talking end behavior here. That's important that you understand that we're not just talking about what's happening around the middle of the function, but what happens as x gets really big or really small. Last year, we used a different notation. For example, we would have written this last year as x approaches negative infinity, f of x approaches positive infinity, and that would be describing that right there. And we would have said as x approaches positive infinity, so as we go right, f of x approaches positive infinity as well, and that would be describing that side of the graph right there. So what we're using now this year is limit notation, and limit notation, which we've used already this year, is saying the exact same thing. As x approaches negative infinity, f of x approaches positive infinity. As we go left, the graph goes up. As we go right, the graph also goes up. It's just that we're using this word limit to say as x gets really big and really small. Same idea, just a little bit different notation. So let's put this end behavior and this limit notation to use here. To describe this end behavior using limit notation, so the first thing we want to look for is that first term. And specifically whether or not the degree is even or odd, and here it's even, and whether or not the leading coefficient is positive or negative, and in this case, it's positive leading coefficient. Let's put LC for leading coefficient. That's the 3 that's right there. So since it's even and since it's positive, we know that this is going to do something like this. We don't know what it does in the middle. We really don't care because we're just talking about the end behavior. So we're going to write this like this. The limit as x approaches negative infinity, and I'm going to do two separate limits here, of this function f of x. And what I'm going to do though is instead of saying that it equals positive infinity, since they both equal the same thing, I'm going to say that the limit as we approach negative infinity equals the limit as we approach positive infinity, which equals positive infinity. I know this year a lot we've been doing this as one limit. If they equal the same thing, we would have written it something like this. I'm going to erase this in a second, but we would have written it something like this. But you're not going to see this very often from our textbook where they put both in the same. They'll do it using this kind of format right there, so I'm going to do the same thing here. Got to get used to limit notation. It's not going away. It's going to get heavier and heavier as the year goes on. We'll take a break from it for a while, but then it'll come back when we start doing our calculus stuff. So take a second and do a little sketch next to example B there to show what you think that this thing is going to look like, this negative x cubed. Doesn't have to be perfect, just a sketch of what the end behavior looks like. All right, now we're going to, well, I'll put a little sketch of what I think it looks like here. It's negative, it's odd. Odd means it's doing something different in both directions. Negative means from left to right, it's going down. Just like negative slope. That would be negative leading coefficient, negative slope with a exponent of 1, which is odd, so it really means the same thing. So what we would say here is, as we go left, or the limit as x approaches negative infinity of this function, all right? Be careful with your limit notation that x approaching negative infinity is small and underneath the word limit. I know it's kind of tough to write it that tiny, but that's what it looks like. That is approaching positive infinity. That is talking about that piece of the graph. Come on. That piece of the graph right there. Then we'll say that the limit as x approaches positive infinity of this function equals negative infinity. And that is describing this piece of the graph right there. Any questions on that at all? Good. All right. All right. Talking about zeros here, zeros of polynomial functions. This is like the pun intended root of what we did last year in Algebra 2 in Chapters 4 and Chapters 5. We started with, before we got into any quadratic formulas or completing the squares, we simply started with factoring, which is what we always want to start with. If it can be factored, you want to factor it. So if f of x equals, I'm going to factor out an x out of this x cubed minus 16x, and x squared minus 16, and that also can be factored because it is the difference of perfect squares. So now we have 3 zeros here. Since my GCF was an x, I'm going to set it equal to 0. And then I'm going to set my other factors equal to 0 as well. I'm going to get x equals negative 4. And I'm going to get x equals positive 4. Which obviously we just write as plus or minus 4. So we have 3 zeros there. It says support graphically. We're going to look more at graphs later on. So I'm not going to worry about doing that here. Just a simple factoring problem. So a little reminder about what the terminology finding zeros means. It means to factor and solve. Finding zeros, same thing as finding roots of an equation. All right, on to the back side. All right, actually, no, go back to the front side of this thing. Instead of us plugging this in, it would take me a second to do it on Desmos. What I'm going to do is see if we can piece together what this function is going to look like. So it says support graphically, which means they want you to pull out your graph calculator, type in, and make sure that it looks like it has those as zeros. But let's just see if we can remember what this graph looks like. So I'm going to plot the zeros on this x-axis here, and go 0 right there, and then we've got a 4, and we got a negative 4. Now if we use our end behavior, which says it's odd and it's positive, we know that this thing is going to look like this from left to right. So using that idea along with the zeros, I think this is going to look something like this. Each of these zeros has a multiplicity of 1. There's no exponent on the factors. This is x to the first, this factors to the first, and this factors to the first. We don't write that, and we normally never even say that. But once we start getting other exponents there, and we have multiplicities of 2 or 3, then it starts changing what happens at those zeros on the x-axis. If it has an odd multiplicity, it's going to go through it, just like all these did. It went through the negative 4, through the 0, and through the 4. But if you have an even multiplicity, it's actually going to be tangent to the x-axis at that 0. So that's a good time. We're going to flip over to this next page now, and we're going to see a few of these that have an even multiplicity. So this asks us to state each zero and then state its multiplicity, and then we're going to graph each. I'm not going to do it on the calculator. We're just going to do it by hand here. So this has a 0 here of 0 from that x equals 0 right there, and it has a multiplicity of 1. And unless if you're asked to state the multiplicity, you don't have to write multiplicity of 1. I'm only doing that because it says state its multiplicity. The only ones that I would state the multiplicity if it has a multiplicity bigger than 1. So like this, what's our other 0 going to be? 3, right? From the x minus 3, set that equal to 0, you get 3, and that has a multiplicity of 2 because of the 2 right there. So what that means is at 3, well right there, Since it has an even multiplicity, we're going to be tangent to the x-axis there. So this thing's going to look a little something like this. Does that match with what we would think about its end behavior? If we were to write this thing in standard form, what would the first term be? Not x squared. Because you got this being x squared, right? It'd be x cubed. So does it make sense that it looks like it does? Yeah, because it's odd, so it's going down here and up there. That is odd end behavior. And it's positive because it would be positive x cubed. All right, take a second and try to find the zeros of the next one, plot them on a graph, and whether or not they're even or odd, figure out if it goes through or is tangent to. And as you do that, I'm just going to fill out these lines down here, which we just talked about. And it crosses the x-axis versus whether it is tangent to the x-axis. We'll take a look at these together. All right, so I have my zeros plotted already. Our zeros are going to be -1, 2, and +4. I suppose I should list here what their multiplicity is. -1 has a multiplicity of 1. 2 has a multiplicity of 2. And the 4 has a multiplicity of 3. So these two are odd multiplicities, which means we're going to be going through the axis, and this one is even, which means that we're going to be tangent to the x-axis there. If I were to FOIL this whole thing out, I think another good thing to write is what that first term would be. This would give us x squared, this would give us x cubed, and if I take x squared times x cubed, that's x to the 5th. And then I have another x right there, which would make this x to the 6th. And then thered be the rest of the polynomial, but all we're interested in is that x to the 6th. It's even, so we know it should look something like that, even and positive. So, if you started thinking, I'm going to come up like this right away, that's actually off, because we want to come down through here. And another thing we could actually find out here, too, is the y-intercept. The y-intercept is where x equals 0. If we let x equal 0, you'd have 1 times -2 squared times -4 cubed. So you have 4 times 64, which I think is 256, positive, right? Oh no, what did I miss there? Yeah, the -4 cubed is -64, right? Change that into that. And I knew it couldn't be positive 256 because it's got to cross somewhere down here. So this isn't to scale at all. This thing is going to be going down through this 0 down to -256. So I'm just going to do that. And then it's going to come back up. And we have a multiplicity of 2 at 2, which means it's going to be tangent. And then we have a multiplicity of 3 at 4, which means I'm going to go back through. I don't know what that is. I don't know what this minimum is. I could find it if I actually plug this into my graphing calculator. I'm sure it goes down further than that because of how far down my y-intercept is. That probably goes down further too. But at least I know what a general idea of this graph is going to look like here. All right, so if you have an even multiplicity, you are going to be tangent to the x-axis, and if you have an odd multiplicity, you are then going to cross through the x-axis. All right, kind of the same idea here. Actually, I think a good idea here is for us to try these on our own, these two here. It's pretty much the same idea. It's putting it all together. We'll kind of do these on our own, and then I'll put up here what the actual answers are, and then we'll kind of talk about them. All right, I have both of these started here with the zeros listed and the degree listed, and now it's time to do a sketch of each. This first one is already in standard form, so we know it's a fourth degree. It's an even polynomial function, and it's positive, so we know that it's going to look something like this in the end. And now that we know the zeros, and we know that it has an even multiplicity at the zero right there, we know it's going to be tangent right there. So it's going to come down through -5, come back up and be tangent at 0, and then go back up through 5. This is an even function. We know if we put -x in for f of x, and you don't have to do this here, just a reminder of what we did last chapter. If we did this, -x in, we get the exact same function back, which means it's an even function. So when we draw it, we can kind of keep that in mind and know that we can fold it over the y-axis. The end behavior, I'm just going to write my zeros on my graph here, -5, 5, and 0. The end behavior is the same, so I wrote that the limit of f of x as x approaches negative infinity equals the limit of f of x as x approaches positive infinity, and both of those equal positive infinity. As we go left, as we go right, it goes up. That's pretty much what that statement says right there. In the last one is h of x. What I'm doing right here is I was just trying to figure out what the degree was if I were to FOIL the whole thing out. So I just looked at the x's that were inside there. There's a linear times what would be a quadratic, which would give me a cubic. And we have a -3 as our leading coefficient, so we know that this is what our end behaviors are going to look like. So without even doing the sketch, I could actually do the end behavior right now and say, as we go left, it goes up. As we go right, it goes down. And we haven't even done the sketch of the graph yet, just kind of this simple little end behavior sketch right there. So our zeros are easier to get in this one because, not that the other one was terrible, but it's already in factored form, so we have that x minus 2 giving us 2 with a multiplicity of 1, and then the x plus 7 gives us, that x plus 7 gives us -7, but because of the exponent of 2, it's an even multiplicity of 2, so we're going to be tangent there. I'm going to use that end behavior and the idea that it's tangent at 7 to start sketching this thing. It's tangent at 7, even multiplicity, and then I'm going to go through the y-axis. I don't think I found the y-intercept. That's okay. I'm going to go through the y-axis somewhere. I could do that kind of dotted thing like I did up above, because I think it's going to go quite a bit higher than that, but that's okay. It's just a general idea of what this looks like. It's just a sketch. So tangent at -7 and through 2. If I did really want to go ahead and find that y-intercept, I could do that by putting in 0 for x and getting -2 times -7 squared. So this is going to be, really, really high up there. Negative times a negative is a positive. -7 squared is a positive, but this is going to be whatever 6 times 49 is, like 294, I think, ish. That's what the y-intercept is going to be, so it's going to be pretty high up there. But we were able to get a sketch, and we were able to get the limits that describe the end behavior without actually finding more than what we have here.